Welcome to Altair Engineering Training and Support. I'm Apur Bapat. Welcome you all in Altair Optimization Contest 2015 Solid Thinking Inspire Contest Model Solution webinar. In this webinar, I'm going to show you how to solve the contest models which we have uploaded for the Solid Thinking Inspire Contest. Actually, I'm not going to solve this model exactly as the problem statement. I'm going to change these values. I'll not put some of the other forces, and I'll make a demo solution of these. So in a similar way, you have to solve these models as these problem has been defined. So I got so many queries regarding the geometry editing of these contest models. So I have divided the contest model geometries into design and non-design part for all the three components. And again, I have uploaded and shared the link with you. I guess everyone has downloaded that updated contest models. And so if not, you can write a mail to edu-support@india.altair.com. At the end, I will share my email ID or the support email ID as well. So you can put a mail if you haven't received that. So we'll start with the problem A, motorcycle. The problem definition and inputs are as follows. Import the solid model of skateboard or the motorcycle in Solid Thinking Inspire 2014. Actually, this point I have now edited, and now you don't have to import the IGS file. You can directly open the STMOD file, which is the extension file for Solid Thinking Inspire. Then make the red color component as non-design and the rest as design. That also you don't have to do. I have done that, and you can directly open a model which will have a design and non-design component. Then create a manufacturing constraint as extrusion. Apply the forces as shown in the image below. Apply the constraint as shown in the image below. Run the baseline analysis, that is linear static analysis. Run the optimization to reduce the weight, but make sure the stress value should not increase by 30%. Then perform the linear static analysis on the final optimized shape. So I'll show you how you can perform these operations on the model provided to you. I will again repeat that the values available here or given here, I'm not going to use the same values. I'm going to edit these values and put a different values, and then you have to put the actual values and solve these models. So I'm just showing how you can solve this model, what are the steps required to solve this model, and accordingly you can solve your contest model. So I will open the Solid Thinking Inspire 2014. Go to Open, Model, browse the file, Part A, STMOD. So this is my file in which I have divided the model in design and non-design part. So you can download this component. So I will start with applying the forces as shown in the image. So first I will apply a force here. But this is the line force. I have applied a surface force. So I will redo it and apply a surface force. Is in the opposite direction. So I will change the direction from here. Apply a 250 Newton force in Z-axis. So if I put a model like this is the XZ plane. So I have applied a force of 250 Newton in Z. Then 2052 Newton on this plate. So I will pick this 2052 Newton, the opposite direction. Then 2016 Newton on this. So I will again apply the force 2016 Newton in opposite direction. Then a central force on this point. So the what it is showing is, I will select this component, and the point is the force is applied on these two sides and the force is applied somewhere here. So I have to create a point. So I will create a point on this, create new surface. So I have created a point. Now I will move this point to somewhat here and apply a force on this point. The direction is x-axis and the magnitude is 18,000 Newton in x direction, and I will create the joinings like this and like this. So I have created some joints like this. So the force is applied on this, both the surfaces. Then I will press A to show all. So in this way it applies the force, you can say. Then a force of 4710 on the center of this area. So force of 4710 on this area, and opposite direction force at the top, at the bottom. So I will create one more point, create new surface, create a point, right click anywhere, then apply a force on this. The direction is correct, that is x, of 12,600 Newton, and constrain it with this and the outer. So you can see I have applied a force in x-axis, and now I am going to apply one more force opposite to this of 15,000 Newton. So I will again create a point on this surface, point on this surface, it is not picking up properly, so I will make sure it picks the proper, and select the center. Now apply a force on this point of 15,000 Newton, and picking this option I will create the connections here and here. So I have created two points and applied the force in opposite direction. Now I will create one more point for this and apply the constraint, forces. So I will create one more point. Let's say I will create a point here. And this is the center point. Now I will move this in the center direction, somewhere outside the body of this. So this is exactly at the center, you can see. Now I will create a force here of 250 Newton in opposite direction and connect it to this end. So I have connected this with this end. Now as I have done with the application of force, I will move to the constraints. So I will first create the constraint at the bottom surface and constrain all the degrees of freedom, and apply a rotational degree of constraint on this location. Making this as free. So I have done with the force application. Now I will save this file and perform the analysis. So I will click keeping all the parameters same as it is, and I will click on analysis. So as I already told you, it will take some time to solve. So till that time, if you have any queries, feel free to ask, as it will take some time to solve and give the results. So now you can see the model is solved now, so you will see the results. So the displacement values on this model and the 1 minus stress. You can also see the animation. You can see the animation on this model. You can increase the scale so that you can see more deformation. So the maximum 1 minus stress is coming as 143.8 Newton per MPa. So I'll stop this, stop the animation, close this, and apply the extrusion constraints. So I will go to this extrusion and apply the extrusion constraint along this, and run the optimization for the weight reduction of 30%, and then we'll see the results of the optimized shape. So if you have any queries related to what does extrusion constraint mean, so I have a video series uploaded already on the YouTube and on the AOC website. Please go through that video series completely to understand these basic concepts behind the theory and all. In those videos I have explained everything regarding the meanings of these terms. If you still find any queries, you can ask me. So again, it will take some time to solve. Okay, so we can see that the optimization has done on this model. So now we will view the results of the optimized shape for this model. So this is the optimized bike frame, you can see, with the 30% weight reduction and withstanding all the loads. So this is the actual weight or actual design. We can modify the design also, and directly we can perform the analysis on this optimized shape, which is what mentioned here. Perform the linear setting analysis of on final shape. So I can directly do the analysis on the final shape and see the results. So this is the optimized shape of my bike frame, and accordingly I can perform the analysis on this. So my actual baseline analysis results for the stresses are 148, and now I'm performing the analysis on this shape and will check the results. If it's more than 30%, so I will change the shape somewhat and then perform the analysis again. So now we are performing the analysis on the optimized shape. So let's see how it goes. So now my analysis has been completed. So I will view the results of the analysis on this. So my von Mises stresses are coming as V lesser than the actual. It's coming as 88.59, so this is lesser than that, and the displacement is also very less. So I will see the animation again. I will decrease it to somewhere around 500. So you can see this is the animation plot. So in this way I have completed this first tutorial. So I will click on new. I will save this. And move to the next one. So the next, that is part B, automobile yoke, says that import a solid model of automobile yoke in SolidThinking Inspire. That thing you don't have to do, and also you don't have to create a design and non-design space. So apply a material as magnesium alloy. Use the manufacturing constraint as single draw and symmetric. Apply 1 Newton meter torque on 2 joints on the top. If I convert that into mm, I'll check accordingly. So I will go to this, open the part B. So I've divided it into design and non-design part, as you can see. So I will make this as design, and the rest others are the non-design part. Now I will make everything, the material for everything, to be magnesium. So I will select magnesium alloy for every part. Then use the manufacturing constraint. But before that, I will run a baseline analysis. After applying torque of 1 Newton meter on the same side, and applying constraints. If it's unfree, that means it's fixed. If it's green, that is it is free to rotate in those components. So I will save this part. And perform the baseline analysis. So this will take some time to perform the analysis. So now as one of my model is solving in this window, so I will solve the other model in another window so that parallelly I can solve the two models. So I'll move to the other one, which is the ball handle. In this, the first two steps we don't have to do. Then the other one, third step, is apply the material as iron alloy cast. Use the manufacturing constraints like single draw and symmetric. Apply a force of 200 Newton on handle both side face such that it resembles a compressive loading. Apply appropriate constraints on both the bolting location. One of the location keep the rotation degree of freedom free. So I will open the model, which is part C. Apply the forces of 200 Newton such that it resembles compressive loading. Apply a constraints fixing all the degrees of freedom. On both the bolt locations. So I have to create one more constraint. So I will apply the constraint here, keeping the rotational degrees of freedom free. Here also the same. On the parts, I will apply the manufacturing and different constraints later on, but before that I will solve this model. So I will increase the element size, say for example 1. So this is done. So I will view the results for this model. Von Mises stresses are coming like this, and I will see the animation plot. The deformation is less, so I will increase the deformation. It's quite less, so I will increase to some more extent. So that it easily visible. I can apply a twisting loading also. Now my problem definition says that I have to apply manufacturing constraint like single draw and symmetric. So I will use the single draw for this direction along or I can use on this direction, and a symmetric along these two axes. And run the optimization. So right now I'm running two parallelly, so that's why it will take some time. In part B, the lower voltage intersecting with the handle won't be affecting the result. No. It is just geographically, or you can say it's just you are able to see this. It is not like that. So it started solving this model. So by the time it's solved, I will wait, and also it is about to start this model. So now I am running two models parallelly. In the part B, I have moved to the optimization, and for part C, I am performing the linear static analysis, and then I will move to a other count. So in this way, why I have used two windows. So just to show you that you can also use 3 or 4 or n number of windows parallelly to solve the models, as it takes some time to solve the models. So parallelly you can work on and try to solve the multiple problems. You can see it started to solve the optimization of this model 2. So as we are running parallelly two models, so it will take some time to solve. So it has solved the model. Now we will see the results. So my von Mises stresses are coming as, the maximum is coming as 2.438, and the displacement is coming as somewhat like this, 0.005, which is very less. So now I will apply the constraints for them, that is, use the manufacturing constraint like single draw and symmetric. So for this, I will apply a symmetric constraint and a single draw along this side, and start the optimization process. So now I have started the optimization process on both the models with the manufacturing constraints. So once it gets solved, we'll see the result and perform the analysis on the optimized shape. Okay, so this is completed now. So we will see the results. So this is the shape. I can manipulate the shape too by changing this bar. I want some additional changes in the shape, I can do that. So I will perform the analysis on this shape and see the values of displacement and stress. By the time it's still running. So as you can see, it started to solve for the linear static analysis on this optimized shape. So the best part of Inspire is you can perform a linear static analysis, you can do the optimization and perform the optimization on the and perform the linear static analysis on the optimized shape very quickly. So I am working parallelly on the two models as you can see, and getting the results done. So as you can see, it has been solved. So we will see the results of stress and displacement. So these are the stress values and displacement values on the optimized shape. I can also fine tune and change the parameters accordingly to get a better results. I will change this value. So about this. So in this way I have ended with the part B. Now we will continue with the part C for the optimization. Once this is done, we will do it for the analysis thing. Okay, so as you can see, this has been completed. So we'll view the results of the optimized shape. So this is what we got as the optimized shape. The nice bead patterns. And now we'll perform the analysis on this. So we can create a connection between that. But this is the optimized shape which is generated with the reduced in the weight. So that's all we want to do in solid thinking, so that we can get a good idealized shape of the structure. So now as you can see, it has been solved for the linear static analysis also. So we will see the results of this for the displacement and the von Mises stresses along with the deformation or the animation. You can see the animation. I put it very high, so I will put it a bit low. So you can see the animation. So in this way, we have ended with this webinar, where I have taken the three models and show them how to solve these models. So in the similar way, you have to solve these models. I'll again repeat the thing is, I am not showing how to solve the exact models. I have just taken the reference from the problem statement and show them how to solve. If you find any queries, feel free to contact us. You can contact me directly on my mail ID, or you can put a mail on edu-support@india.altia.com. Thank you very much for attending this webinar.